The final topic that we're going to have a look at in Gaussian quadrature is the GaussHermite quadrature. Again, this is a method for improper integrals. So the GaussHermite formula comes from the following quadrature rule. It's an integral from minus infinity to infinity. There is a weight function w of x that is equal to e to the minus x squared, and again it's just equal to a sum over n, where n is the number of points in our quadrature, of the weights ai multiplied by the function evaluated at the quadrature points xi. So the parameters again are chosen so that the rule is exact for polynomials up to and including degree 2n minus 1. For example, when n is equal to 2, we come up with these four equations here. I'm not going to go through the derivation of that, it's not that important. If we solve those, we see that a1 is equal to a2 is equal to pi on 2, and that x1 and x2 are equal to plus and minus 1 on root 2. So this is symmetric about the origin, this particular quadrature rule. And again, for reference, the xi are the roots of the nth order Hermite polynomial. Again, a polynomial that comes out of physics and the real world. And the ai, the weights, are obtained from derivatives of these polynomials. So for n is equal to 2, which is the case that we're looking at here, the yellow polynomial has roots here and here, so plus and minus 1 on root 2. As with the Gauss-Laguerre quadrature, we can rearrange our functions so that we can actually apply a Gauss-Hermite quadrature, because we need the e to the minus x squared. So just as we did with Gauss-Laguerre, we can see that we can multiply any function by e to the minus x squared times e to the plus x squared. And if we churn through this, we see that our integral from minus infinity to this is just equal to the sum of the quadrature points of our weights times e to the xi squared, that comes from there, times the function values evaluated at xi. So Gauss-Hermite you can use to do indefinite integrals over the entire real line.